Okay, you should have your notes for Lecture 40, An Unusual Value May Change Your Mind. All right, we've been talking about unusual values, tail probabilities, t-scores, that sort of thing. We are now going to start looking at a very powerful practical application of those ideas, and it's called hypothesis testing. And in subsequent lectures, we're going to develop that idea very formally and thoroughly. But this lecture, I just want to kind of give you an overview of the main ideas without getting too wrapped up in some details. We'll look at a few details in the next lecture where we do some computational stuff. But if we have this lecture where we get kind of some of a big picture, and the next lecture where we do some computations without really formally introducing it, all the notation, then we'll be ready to see it in its entirety with all the right notation and everything, and I think it'll be less confusing that way. So I just want to, like I said, start off by just giving you a general idea. Okay, so starting here at Lecture 40, suppose a certain kind of tomato plant yields a mean of mu sub 0 pounds of tomatoes per plant with a standard deviation of sigma pounds. All right, so I don't want to put actual numbers to this again because I don't want us to get bogged down into actually doing computation. So just think of mu sub 0 as some number of pounds, maybe 18 pounds on average per tomato plant. And that mu sub 0, mu we know represents a population mean. So I'm thinking of all these tomato plants. I'm looking at all their yields in pounds, and I'm taking the mean of all of them, and we call such a population mean. We use the symbol mu, and the mu sub 0, or mu naught, sometimes I say, is a way of just referring to the first mean that we're talking about. We are going to see that under certain circumstances, we're going to maybe have that mean take on a different value. But starting off, we're calling it mu sub 0. So the sub 0 is just kind of a way of saying, this is our first value that we're looking at, the initial value. All right, so anyway, we have a mean of mu sub 0 and a standard deviation of sigma pounds. If W then is the weight in pounds from a randomly chosen plant, weight in pounds of tomatoes, right, from a randomly chosen plant, then taking samples of size n, for n bigger than or equal to 30, will give us, by the central limit theorem, it'll give us that the sample mean random variable, W bar, will be able to be taken as being normal with mean mu sub 0 and standard deviation sigma over the square root of n, where, again, n is the sample size. We're not starting off assuming that the tomato plants themselves give yields that have a normal distribution, right? They may or may not, but we're assuming that we have a big enough sample then that the sample means would give rise to a random variable that is normal with the same mean, mu sub 0, and that smaller standard deviation, sigma over the square root of n. So again, this means I take a sample of size n and I compute the sample mean. And then I take another sample of size n and compute the sample mean, and take another sample and compute the sample mean. I get all these different values for the sample mean. I'm generating a random variable from all those random samples, and that's what we expect the probability distribution to be. And what's the PDF look like? The probability density function, or the probability curve, something like this. So here's mu sub 0, and we have our bell curve, and somewhere in here maybe is what the standard deviation would be for the sample mean, which is sigma over the square root of n, sigma being the sample for the population of yields per plant, and so the standard deviation for W bar is sigma over the square root of n. Okay, now I say here, suppose we introduce a new fertilizer for all these tomato plants. All right, so we have all the plants, we introduce this new fertilizer, give it to all of them, and what that does is it creates a new population of pounds of tomatoes yielded per plant, right? So we have this new population of data now. And of course, we're entering the fertilizer with the hopes that we're actually going to increase the yield per plant, right? That's what I say down there. So we're doing this in the hopes of increasing the yield per plant. So suppose we were just to do that to all the tomato plants. We'd have a new population of yields, and we'd have potentially a new value for the mean yield per plant. So I say here there are two possibilities. Number one, fertilizer doesn't work. Fertilizer does nothing. Okay, so it does not change the yield per plant. So what do we expect to see? Then we expect to see that before the fertilizer, before we have that bell curve, and after we change all the plants by giving that fertilizer, the new curve we have for all the different yields from the plants is same as before. The mean didn't change in particular. All right. Other possibility, 2, fertilizer does work. So what happens there? I think I can squeeze this in. Before we have, let's see, how far can I go? I can go to there, that's good. I'm kind of running out of room. This says mu sub 0 there. I've run out of room. Sorry, it's off the bottom, but that right there says mu sub 0 under it, and we have our bell curve like that, as before. But then after we introduce the fertilizer, let me bring it up a little bit just so I have room below. What I have here is I have my mu sub 0, and it's barely on there. That's mu sub 0. But what's happened is, in fact, we have a new mean, mu, and so our curve now looks like this, right? It's now like this. It's supposed to be the same curve, except shifted over. Okay, so so I guess I don't need to write anything more here. I just want to say, if the fertilizer doesn't work, then we just expect that we get basically the same probability curve before and after. If the fertilizer does work, here's our before curve, here's our after curve. The new mu, which is right there, is bigger than mu naught, right? So let me just say the new mu is bigger than mu sub 0 in this case, right? And down here, the mean stays the same. I won't even bother to write that. Okay. So yeah, I guess I want to just, maybe I do want to stress, get it in here for the sake of completeness. I would go below if you have room, but I'm going to have to write it right here. The new mu, how did I word it here? Just the new mean mu is the same. Mu equals mu sub 0, okay? And like I said, it looks better if you put it below, but I just run out of room. But the new mu over here is bigger. And actually, this is wrong because this is before. Doggone it. It should be up here, right? The new mean mu is the same. Mu equals mu 0. All right, this is if it doesn't work, the new mean is still the same. If it does work, the new mean has shifted and it's bigger than mu sub 0, than the original one. All right, well, which is it? Well, I say here in the next couple of paragraphs here in the middle of page 2, before we commit to using this new fertilizer on all our plants, generating a whole new population, we'd like to know which of the above scenarios is true. If the fertilizer isn't going to work, I don't want to use it. If it is going to work, I do want to use it. So we'd like to test somehow whether or not the mean yield per plant, mu, will be larger after applying the fertilizer. How do we do this without applying the fertilizer to all the new plants, thus generating a new population? How do we do that without, going wholesale and spending all the money and everything to see and maybe discover that it makes no change? Well, what I say is let's try the following. Let's take a simple random sample of size n of plants and apply the fertilizer to each plant in the sample. So I grab a sample apply the fertilizer to it, and what I've really done is it's kind of like I've applied the fertilizer to the whole population, and now I'm taking a sample from the new population, right? When I take a sample and apply the fertilizer, I'm sort of taking a sample from what would have been the new population if I had applied it to all the plants. So what we'll do is we'll let the plants grow, and then we'll measure the yield for each plant and compare W bar, the mean weight for this sample. We'll compute W bar, the mean weight for this sample. What do we expect to happen? Well, what we're going to do, we're going to look at the possibilities for that, and we're going to look at them in the context. We'll ask this question in the context of our original PDF curve. That is, we'll ask the question under the assumption that the population mean would not shift if we got the new population of tomato plants, but would just stay the same. All right, so here's one thing that could happen down there. So first off, this could happen. Let's see. So in the context of there being no change, so I have my original probability curve, right? There's my original mean. There's no change. I compute the sample mean from this new sample where I've applied the fertilizer, and what I find is I compute W bar, the sample mean, and I find that W bar is maybe way out here, all right? Okay, well, what that means is, or what that indicates here is, look, I have a very small tail probability, right? Small tail probability or small tail area, all right? So W bar is, and I think I want to say, yeah, W bar is unusually large, right? Assuming that the mean hasn't shifted. Assuming the new mean mu is equal to mu sub 0, right? All right. So, so assuming the population stays the same, it's an unusually large value because it's out here with a small tail probability. So under the assumption, I now say that the probability curve hasn't shifted, that the mean hasn't changed, we get that this W bar is an unusual value. But here's the key. Since we just grabbed this sample, applied the fertilizer, we would not usually expect to get an unusual value. For whatever the true population curve now is, the true bell curve is, we would expect to get a usual value. Typically, you don't get unusual values. You may get an unusual value, but typically you don't. So the fact that we actually got that usual value for the mean, we don't expect it to be an unusual value. So what that does is it suggests that the post-fertilizer population mean mu may be greater than the original mean mu. So this suggests that really, that this is wrong. It suggests, I guess I can fit it in right here. Here's my mu 0, and out here is my W bar. But it suggests that maybe there's the new true mean, so that my curve is more like this, right? So I have not so small tail area. Not so small tail probability. I say tail area just because it's quicker to write than probability. Okay, so suggests the new mu is larger than the original one. All right, so it suggests that the fertilizer actually worked. Okay. Now, I guess I'll just stress at this point, I don't know for sure that it has worked. I can get an unusual value, right? I can take a fair coin and toss it 10 times. It can come up heads every time. That can happen. It's not impossible, but it would be unusual. That would suggest to us maybe the coin isn't fair. Likewise here, I get such an unusual value for W bar that though that's a possibility to get that even if the mean hasn't changed, I'm way out here, it suggests that no, really what's going on is, and it looks like my hump is right here, so my new mu should be about right there, right? I'm off a little, but It's supposed to be centered right on there. But my whole point is that the mu shifted over, and so my W bar now is more like what we would expect. We'd expect to get this more what we would call a usual value for W bar with a not very small tail probability, okay? The small tail probability suggests that I should change my mind about where I think the new mean is. I don't think it's here. I think it's maybe more over here. I don't know exactly where to put it, but I do think it's bigger than mu naught. Okay, that could happen. Number two, what could happen? Or number two, what could happen is here is my mu naught. Let me go ahead and put the curve in. All right, and maybe W bar just lands there. So I have a not so small tail probability to begin with. Okay? It's a not so small tail probability to begin with. This suggests that, well, look, my sample mean is a little bit bigger than mu naught, so that might indicate that, in fact, the yield per plant, the mean yield, is bigger. It might indicate that, but I don't have a strong reason for believing that, because this value of W bar that I got here is not an unusual value, assuming that the mean didn't change at all. So I don't have something here, but looking at that value and saying, wow, that's a really strange value to get, probably means the mean is different. It's not so strange. Maybe the mean is the same. So how did I word that? I think I said not so small tail area, and so it's not so unusual. So I guess I have it typed out there that this does not strongly suggest that the new population mean would be larger than mu naught. Okay, so I have the case where I get this unusual value that suggests the curve's probably shifted. I got a case where I didn't get an unusual value. That doesn't suggest that the curve didn't shift. It just doesn't give me a strong reason to say to you, yeah, I think it shifted. Up here, yeah, I have a strong reason to think that I should shift it over to give you that, something more like that. Down here, I just don't have such a strong reason. Okay. So assuming, about ready to quit here. So assuming that the population mean is of a certain size, and then getting an unusual value for a sample mean suggests that the assumption about the population mean may actually be wrong. And the value of the population mean may actually be closer to what the sample mean's value is, right? I get this unusual value. Probably that's wrong, and I should somehow slide it over closer. I get this not so unusual value. That may not be wrong. I don't have a good reason to slide it, right? Okay. Let's see, not so unusual value mean suggests that the assumed value mean may be correct. How do we decide what's an unusual value and what isn't? All right, how do we decide? It's just looking way out here. It looks like it's unusual, and this one down here looks like it isn't very unusual, but we need a tight criterion for saying whether or not a value is unusual or not. And the answer is we can start with a cutoff tail probability, and I'm going to go ahead and call it alpha, since that's what we will be calling it later on. So I have a cutoff tail probability of alpha. And so let me just say it in English, and let me just draw the picture. If we calculate the tail probability of, in this case, our sample mean, and that tail probability is smaller than what we're going to call our cutoff value for unusualness, we would say it's unusual. Hence, probably the mean should be bigger. The population mean should be bigger. If the tail probability we compute for our W bar is not smaller than alpha, that's going to indicate it isn't out far enough for us to think of it as unusual, and we don't have a good reason for suggesting that the new mean is different from the old mean. So let me draw those pictures. So we have two possibilities. Let me just say colon here. So we can have this. So how do I word it? I guess here's my mu naught. All right, and here's that. And I have somewhere out here, I guess maybe I can use all different colors, why not? Somewhere out here, I have some cutoff value because this tail probability equals alpha. All right? And what I might have happen is, I think orange will work. I might have W bar being out here. It's same color. Let me try this. Actually, let me try this. W bar could be here, and my W bar's tail probability, which is this here, I'm not going to color it. Well, I can kind of W bar's tail probability or tail area is less than alpha. Makes us think that W bar is unusual, makes us think nu mu is really greater than mu naught, right? Okay, or contrast this with, or we have our mu naught here. Okay, my curves are a little bit sloppy. And again, I have my, keep the colors the same. Way the heck out here, I have some cutoff value and tail area equals alpha. And this time, my W bar is in here, and my tail area then is all that. So W bar's tail area or tail probability is greater than alpha. Let's just say it like this: doesn't give. Better move over here. Doesn't give a good reason for thinking the new mu. Running out of room. The new mu is larger than mu naught. Okay, so I say we can start with the cutoff tail probability. Typically what happens in an application, we'll see this again and again, we will be given, or we will have a way of coming up with what we're going to call our unusualness value. In the past, we've said 5% for the tail area, right? That will change depending on the context now. But we will, walking into a problem, we will often have a cutoff probability. And then the goal will be to figure out our value of our in this case, our sample mean, and just figure out what is its tail probability. Is it less than alpha? If so, we believe that the mean is shifted. If it's not less than alpha, we can't really have a strong reason for saying that the mean shifted. Okay, next lecture, we'll put this to numbers, so I think it'll maybe solidify a little bit more. But try to keep in mind this overall picture. If you keep this overall picture in mind, then you won't get so bogged down in the details when we develop this more thoroughly. All right.